we are going to discuss about the topic change of variable, where we are going to discuss about the content of Jacobian of transformation also. So, before we'll start with the topic of the Jacobian of transformation, let me firstly tell you the what is the Jacobian of transformation. The Jacobian of transformation means that when we transform one set of variables into a new set of variables, right, then we need a transformation factor that is called a Jacobian of transformation. For example, when we transform a set of variables, say x and y, to a new set of variables, say u into v, right? So when we transform one set of variables into a new set of variables with the help of some transformation, say we have x is the function of u and v, and y is the function of u and v. When we make this particular kind of a transformation, then we need a transformation factor. Especially, we use this particular concept in the case of integration. To understand this particular concept, I'm considering a simple example of single integration. Suppose I want to integrate my function sine of 2x dx, right? I want to integrate this function. So here we know that the integral of sine x dx is minus of cos of x plus c. But here instead of sine x, we have a function sine 2x. So what can we do? So to use this particular identity, I'm going to transform this particular variable into new variable. So for that particular purpose, suppose that I make a transformation, let 2x is equal to t. So what about x is equal to t by 2? And what about dx? This is equal to 1 by 2 times dt. So if we use this particular transformation, then this will be equal to sine of t, and this dx become dt by 2. So in this case, basically this integral is converted into sine of t into this 1 by 2 is a transformation factor, so that these two will be equal. So to balance this variables into this particular form, so we have used this particular transformation that we have replaced, we have the transformation like 2x equal to t. But when we do this kind of transformation, then to balance this particular two part, so we need to add one transformation factor. So here the transformation factor is 1 by 2. 1 by 2 is that is dx upon dt. This is called the Jacobian or transformation of x with respect to t. So in the same way, if we have a set of variables, say we have a two variables, and I want to transform it into new two set of variables u into v. So in that case, for example, I have a function f of x, y, dx, dy, and I am going to transform it into new set of variables u, v by using such kind of transformations. This is capital F. So my new function will be g of uv. But when we transform this, then dx dy, and we transform it into du dv, then we need a transformation factor which is called a Jacobian of transformation. So what is the Jacobian of transformation? In this case, this is the Jacobian of xy with respect to uv. And how we are going to calculate this? This can be calculated with the help of the formula that the partial derivative of x, because x depend upon more than one variable, y also depend upon more than one variable. So it can be calculated as curly x upon curly u, first with respect to first and first with respect to second. Curly x upon curly v. Similarly, curly y upon curly u, curly y upon curly v. So this is how we can calculate the Jacobian of transformation of the two variable x and y with respect to u and v. Right? Let us consider one problem here. So suppose that we transform x equal to r cos theta in a polar coordinate system. We use this transformation y equal to r sin theta. So when we transform this, then what is the Jacobian of transformation in this case? Jacobian of transformation means curly of xy with respect to r and theta. So if we calculate this, its value comes out to be curly x upon curly r, curly x upon curly theta, curly y upon curly r, curly y upon curly theta. So what is the derivative of x with respect to r? When we differentiate with respect to r, then theta is treated as constant, so its derivative is cos theta. Similarly, if I differentiate x with respect to theta, then r is treated as constant, derivative cos theta is minus of sine theta. This is minus r sine theta. Similarly, if we calculate derivative of y with respect to r, it is equal to sine theta. And if we calculate derivative of y with respect to theta, its value is r constant, derivative of sine theta is cos theta. So its value comes out to be r times cos theta. So if we substitute this value here, so what is the derivative of x with respect to r? It's cos theta. This is minus r sine theta, and derivative of y with respect to r, this is sine theta, and this is r times cos theta. So if we expand this determinant, this comes out to be r times cos square theta plus r times sine square theta. So we know the identity that cos square theta plus sine square theta is equal to 1. So its value comes out to be r. So what do we conclude from here? That Jacobian of xy with respect to r and theta in case of polar coordinate system, its value comes out to be r. Okay, let us consider another example. Another example is suppose in case of spherical polar coordinate system, we make the transformation as x equal to r sine theta cos phi, y is equal to r sine theta sine phi, and z equal to r cos theta. And we want to find out the Jacobian of transformation in this case, that is Jacobian of x, y, z with respect to r, theta, and phi. This is equal to curly x upon curly r, curly x upon curly theta, curly x upon curly phi. In the first row, x with respect to first, second, and third. Now, similarly, y with respect to r, y with respect to theta, y with respect to phi. Now, z with respect to r, z with respect to theta, and z with respect to phi. So, the derivative of x with respect to r. If I differentiate with respect to r, then theta and phi, they are treated as constant, which means this whole term is constant, and derivative of r with respect to r is 1. So its value comes out to be sine theta cos phi. And if I differentiate this function, with respect to theta, if I differentiate with respect to theta, then r and phi, they are treated as constant. The derivative of sine theta is cos theta. Derivative of sine theta is cos theta, and derivative of cos theta is minus of sine theta. So basically, we are going to use only these three identities. So its value comes out to be r times derivative of sine theta is cos theta cos phi. Similarly, if I differentiate with respect to phi, then r and theta constant, derivative cos is minus sine. So its value comes out to be minus r sine theta sine phi. Similarly, now when we differentiate y with respect to r, so this is sine theta, there it is sine phi. Let me correct this. This is not theta, this is phi. And if I differentiate with respect to theta, then this is r times cos theta sine phi. And if I differentiate with respect to phi, this is r times sine theta cos phi. Now come to z. It depends only on r and theta. If I differentiate with respect to r, then its derivative is cos theta. If I differentiate with respect to theta, minus r sine theta. And if I differentiate with respect to phi, because it is independent of phi, so its derivative is 0. So now we need to expand this determinant. So we need to expand through third row because already one of the term is 0. Let us expand through third row. So firstly, we can write it as cos theta into this. So r cos theta cos phi into r sin theta cos phi. This minus is already there and minus become positive. R sin theta sin phi into r cos theta sin phi. This is the coefficient of cos theta. Now come to the second term. Second, we expand through this one. So this into this. So its coefficient is already, because this is the position A32. A32 is minus 1 raised to the power 3 plus 2 is negative, and its coefficient is minus r sin theta already there. So now when we expand this into this, it is already 0. Sorry, this into this. So sin theta cos phi, sin theta cos phi into r sin theta cos phi, r sin theta cos phi. And again, this minus and minus become plus sin theta sin phi into r sin theta sin r sin theta into sin. Now, let us solve this particular expression here. So what do we get? So the Jacobian of transformation, this is cos theta as it is. If we open this, r into r is r square, cos theta sin theta, cos theta sin theta into cos square. And here again r into r square, sin theta into cos theta, sin theta into cos theta is there into sin square, into sin square. Now plus this negative become positive, plus r sin theta as it is. Inside the bracket is only one power of r, and now sin theta into sin theta is sin square theta, and here cos phi into cos phi is cos square phi, plus this side again r is only one r is there. So sin theta sin square theta into sin phi sin square phi. So here you will find out there that r square cos theta sin theta, r square sin theta cos theta. This is common. So what we left with cos square phi plus sin square phi. And we know that cos square theta plus sin square theta is 1. So cos square phi plus sin square phi is also equal to 1. So this is 1. So we left with cos square theta. So it will gives us, here cos theta is already there. And we need to take common r square cos theta into sin theta. Right? So this is from the first term. And what about the second term? R sin theta is already there. r sine square theta, r sine square theta common. We left with cos square phi plus sine square phi, which is again equal to 1. So it is r sine theta into r sine theta 1 is already there and r sine square theta. So this is r square sine cube theta. So what is the value of r? This is r square cos square theta sine theta plus r square sine cube theta. And here again r square sine theta is common. So we get cos square theta plus sine square theta. Again cos square theta plus sine square theta is 1. So its value comes out to be r square sine theta. So what is the Jacobian of transformation in this case? Its value is r square times sine theta. Okay, so this is the Jacobian of transformation of two well-known results, which we are also going to use in the multiple integral part, especially when we transform Cartesian coordinate into polar coordinate system or Cartesian coordinate into spherical polar coordinate system. Then we'll use these two Jacobian of transformation. Okay, so before we proceed, firstly we'll discuss some properties of Jacobian of transformation. So properties of Jacobian of transformation. Okay, the first property is if J is equal to say Jacobian of x, y, z with respect to u, v, w, and say J dash is Jacobian of u, v, w with respect to x, y, z, then J into J dash is equal to 1, or we can say that J dash is 1 upon J. What does that mean? So for example, we are using x equal to r cos theta and y equal to r sin theta. This is the transformation we are using. And we have calculated Jacobian of transformation with respect to xy with respect to r theta, it comes out to be r. But suppose I want to find out Jacobian of r theta with respect to xy. Then what is value? It is simply the reciprocal of j. So it is 1 upon r. But of course, in that case, we are expecting value in term of x and y. So what is r? Scaling and adding. We scaling and adding, then we get r square equal to x square plus y square. So the value of r is square root of x square plus y square. Okay, but we can directly get it rather than firstly calculating the value of r in term of x and y, theta in term of x and y, and then solve the Jacobian of transformation. If the Jacobian of transformation of one of the term is known, then we can find out the other one using this property, right? This is the first property, the Jacobian of transformation. Second one is if the Jacobian of transformation, say x, y, z with respect to u, v, w, or we are having two variables is equal to 0, it means that the variables, x, y, and z are functionally related. Functionally related. It means that there is some relationship between the variables x, y, z. Okay. Like otherwise, we are saying when I say x equal to r cos theta, y equal to r sin theta, then we are saying that x and y are independent variables. R and theta are also independent. But if the Jacobian of transformation of set of variables comes out to be 0, it means that these variables must be functionally related, right? Okay, let us consider an example to understand this problem. Suppose the question is, suppose that we are given u equal to, suppose that we are given u equal to tan inverse x plus tan inverse y, and v is given as x plus y upon 1 minus x into y, where x and y greater than 0 and x into y is x into y is less than 1. So we want to know that whether the variables are functionally related, whether the variables are functionally related. So how we are going to check here? So we simply check Jacobian of transformation, that is Jacobian of u with respect to x and y, which is equal to curly u upon curly x, curly u upon curly y, curly v upon curly x, curly v upon curly y. So what is the derivative of u with respect to x? U equal to tan inverse x plus tan inverse y. So what is curly u upon curly x? When we differentiate with respect to x, then y is constant, so derivative of tan inverse y is 0. But tan inverse derivative is 1 upon 1 plus x square. What about derivative of u with respect to y? This is 0 plus 1 upon 1 plus y square, because derivative of tan inverse x is 1 upon 1 plus x, right? Now we are going to calculate the derivative of v with respect to x and y. So here we are using the quotient rule, right? So what is the derivative of u upon v? So derivative of u upon v. This is v squared, v time derivative of u minus u time derivative of v. So we are going to use this property here. So this is 1 minus xy as whole square. So 1 minus xy as it is. Derivative of x plus y with respect to x. Its derivative with respect to x is 1, and derivative of y with respect to x is 0. Minus x plus y as it is. Derivative of 1 is 0. Derivative of xy with respect to x is minus of y. So if we solve this, this is 1 minus xy plus xy plus y square upon 1 minus xy whole square. So this is 1 plus y square upon 1 minus xy whole square. This is curly v upon curly x. Okay. And similarly, we can find out curly v upon curly y. And if you remember in our last video of chain rule, we have discussed that if your function is symmetry, that means if we interchange x and y, if your function remains same, then if one of the derivative is known, we can find out the other one by simply interchanging the variables. Means its value comes out to be 1 plus x square upon 1 minus xy whole square. Otherwise, we can calculate with the help of the formula also, that 1 minus xy whole square, 1 minus xy, derivative of x plus y with respect to y is 0 plus 1. And now this time x plus y as it is, derivative of 1 minus xy with respect to y is minus x. So this will comes out to be minus xy plus x square plus xy upon 1 minus xy whole square. So xy cancel out. So this is 1 plus x square upon 1 minus xy whole square, right? So either we can directly calculate this particular result, or we can use the formula also. But like I told you, when we solve MCQ type problems, then we need to save our time. Okay. So if we substitute these value here, so what do we get? Curly u upon curly x is 1 upon 1 plus x square. This is 1 upon 1 plus y square. This is 1 plus y square upon 1 minus xy whole square. And this is 1 plus x square upon 1 minus xy whole square. Now if we solve this determinant, and this is this into this, 1 upon 1 plus x square into 1 plus x square upon 1 minus xy whole square minus 1 upon 1 plus y square into 1 plus y square upon 1 minus xy whole square. So 1 plus y square, 1 plus x square cancel out. So its value comes out to be 1 upon 1 minus xy whole square minus 1 upon 1 minus xy whole square. Cancel out, answer comes out to be 0. So what do we conclude from here? That the Jacobian of transformation is 0. And according to the property of the Jacobian of transformation, if the Jacobian of transformation is 0, it means that the variables are functionally related. So what do we conclude from here? It means that u and v are functionally related, means they are not independent variables. Okay. So this is how we can prove it with the help of the Jacobian, but otherwise we can use the property of inverse trigonometric function also, that tan inverse x plus tan inverse y. If we use the trigonometric identity, this is tan inverse of x plus y upon 1 minus xy. This is the property of the tan inverse. So it comes out to be tan inverse v, right? Otherwise, we can prove it in this way, let tan inverse x equal to a, tan inverse y equal to b. That what is tan of a plus b? So here we use the formula of tan a plus b is tan a plus tan b upon 1 minus tan a into tan b. So what is tan of a plus b? So this is tan of a plus b. So tan a it is x and tan b is y. This is x plus y upon 1 minus xy. If we apply inverse transformation, then a plus b is equal to tan inverse of x plus y upon 1 minus xy. And what is a plus b? This is tan inverse of x plus tan inverse of okay. So this is the proof of the inverse trigonometric identity. So here we have proved that if the variables are functionally related, then the Jacobian of transformation is 0 also, right? Okay. So here we have discussed the problem that how do we calculate the Jacobian of transformation for two variables or three variables, or how do we check that the variables are dependent or functionally related or not, right? Now, there is another form of the Jacobian of transformation problems also. Another form of problems is sometimes the question is asked like in the if you remember in the chain rule we have discussed that if x is a function of sorry if z is a function of x and y, and x and y they are further function of u and v. X and y they are further function of u and v. So it means that x and y they are also then z is also function of u and v, right? But if the question is we are given f is a function of x and y, and x and y are function of u and v, but we need to express curly f upon curly x in term of u and v, and curly f upon curly y in term of u and v. Then again we are going to use the concept of change of variable. So what is the criteria there? So here we use the chain rule formula that what is curly f upon curly u. This is curly f upon curly x upon curly u, curly f upon curly y upon curly u. This is the chain rule property number 3, case 3. What about curly f upon curly v? This is curly f upon curly x upon curly v, curly f upon curly y upon curly v. That f is a function of x and y they are function of u and v, then f is a function of u and v with the help of this chain, right? But what I want to do, I want to express curly f upon curly x and curly f upon curly y in term of u and v. So it means that these are our unknown, and we need to express it in term of u and v. So I'm assuming it as a system of equation. So we can apply cross multiplication method to find out the value of curly f upon curly x and curly f upon curly y. So this is minus 1. Applying 2, 3, 1, 2 method. This is 1, this is 2, and this is right inside 3. Okay. So firstly, we are applying 2, 3, 1, 2 method. 2, 3. This into this. So curly y upon curly u into curly f upon curly v minus curly f upon curly u into curly y upon curly. So this is 2, 3, 1, 2 method. Firstly, we consider 2 and 3. 2 and 3. Then 3 and 1. 3 and 1. So curly f upon curly u, curly x upon curly v minus curly x upon curly u, curly f upon curly v. So what we have done, I simply write the coefficient. This is 2. Second number coefficient is curly x upon curly u, and here it is curly x upon curly v. Number 3 is curly y, sorry, this is the second number. The coefficient of second number term is curly y upon curly u, curly y upon curly v. Number 3 coefficients are the right hand side, means the other side term. Curly f upon curly u, curly f upon curly v. Then number 1 is curly x upon curly u, curly x upon curly v, and again number 2, curly y upon curly u, curly y upon curly v. So this into this minus this into this. This is the first term we have written. Then this into this minus this into this. This is the second term. And third term is this into this curly x upon curly u, curly y upon curly v minus curly y upon curly u, curly x upon curly v. Right? So if you just check this particular part, this is nothing but the Jacobian of xy with respect to u. Right? So this is nothing but Jacobian of transformation with respect to u and v. Right? To get the value of curly f upon curly x, so we compare first with third. And so if I compare, then what do we get? So we can get curly f upon curly x equal to minus 1 upon j time. This is curly y upon curly u, curly f upon curly v. So this is also Jacobian, but this is Jacobian of yf with respect to uv. As you can see here, y with respect to u, f with respect to v, then f with respect to u, y with respect to v. First, this into this, this into this. If you just look at here, this is the Jacobian of yf with respect to uv. Okay, and this is the Jacobian of fx with respect to uv. So what is the value of curly f upon curly y? This is minus 1 upon j Jacobian of fx with respect to uv. So here, if I want to adjust this negative sign, we know that this is nothing but determinant. If we adjust this negative sign, it means that we simply need to interchange a position. So it means that this is 1 upon j times Jacobian of fy with respect to uv, because what is the Jacobian of fy with respect to uv? This is curly f upon curly u, curly f upon curly v, curly y upon curly u, curly y upon curly v. So if I interchange two rows, it means that we need to adjust one negative sign to balance the value of the determinant, right? So similarly, here also if I want to adjust this negative sign, so I can write 1 upon j times Jacobian of xf with respect to u. So now this is the formula if we transform xy into u. So how do we calculate curly f upon curly x with respect to in term of u and v? So it is easy to remember this formula. So what can we do? So for example, I want to find out curly f upon curly x, right? So what is j? J is the Jacobian of xy with respect to u, right? So if I want to find out curly f upon curly x in term of uv, so of course 1 upon j is required. But in this case, if I want to calculate curly f upon curly x in the Jacobian of transformation formula, we are going to replace x with f. So what do we have? Jacobian of fy with respect to uv. Okay. And if I want to calculate curly f upon curly y, so again 1 upon j as it is, but this time I'm going to replace y with f. Curly f upon curly y means replace y with f. So we'll get Jacobian of xf with respect to uv. So this is the formula for the Jacobian of transformation if we are going to replace two variables. Okay. So if you understand this concept, then you can extend this formula for any number of variables also, right? For example, suppose that we have a relation of x, y, z with u, v, w, but you need to find out curly f upon curly x in term of u, v, and w. So what should be the formula? So this is 1 upon j. So what is j in this case? Jacobian of x, y, z with respect to u, v, w. So what we are going to do? We are firstly going to replace curly f upon curly x means replace x with f. Jacobian of f, y, z with respect to u, v, w. And if I want to calculate curly f upon curly y, so what about curly f upon curly y? Replace y with f. 1 upon j times Jacobian of x f z with respect to u, v, w. And if I want to calculate curly f upon curly z, replace z with f. 1 upon j Jacobian of x y f with respect to u, v, w. But if I want to place x f at the first position, means I simply need to interchange this. One interchange means we are interchanging one column, sorry, one row. So it means minus of Jacobian of f x z with respect to u, v, w. And in this case, it means that we need to shift two places. So this is again positive 1 upon j Jacobian of f x y with respect to u, v, w. So this is how we can calculate the value of curly f upon curly x, curly f upon curly y, or curly f upon curly z in terms of the other set of variables, right? Okay, let us consider one problem here so that we can understand that how can we use this concept in a problem of change of variable. Suppose the question is, suppose the question is, if that is a function of x and y, that is the function of x and y, and x is equal to r time cos hyperbolic theta, and y is equal to r sine hyperbolic theta, then find the value of curly f upon curly x square minus of curly f upon curly y square in terms of r and theta. Okay, so we are given that f is a function of x and y, and x and y is a function of r and theta. But we want to find out curly f upon curly x and curly f upon curly y in a term of r and theta, right? So let us see how do we calculate in this case. So what can we do here? So here because x and y they are given as a function of r and theta. So we are going to use the concept of change of variable. So what is curly f upon curly x? So here we use the concept that this is 1 upon Jacobian of transformation. So Jacobian of transformation will be Jacobian of xy with respect to r and theta. So this will be Jacobian of fy with respect to r and theta, and curly f upon curly y is 1 upon Jacobian of transformation time Jacobian of xf with respect to r and theta. So what is the Jacobian of xy with respect to r theta? Because firstly we need to calculate j. So this is curly x upon curly r, curly x upon curly theta, curly y upon curly r, curly y upon curly theta. So what is the derivative of x with respect to r? This is cos hyperbolic theta. And derivative with respect to theta. So what is the derivative of cos hyperbolic theta? Basically, cos hyperbolic theta is e raised to power theta plus e raised to power minus theta by 2. And sine hyperbolic theta is e raised to power theta minus e raised to power minus theta by 2. So in this case, derivative of cos hyperbolic theta is sine hyperbolic theta, and derivative of sine hyperbolic theta is cos hyperbolic theta. You can differentiate, you can get this result, right? So what is the derivative of x with respect to theta? It is r times sine hyperbolic theta. And derivative of y with respect to r is sine hyperbolic theta. And derivative of y with respect to theta is r cos hyperbolic theta. Now, if we expand this, r times cos hyperbolic square theta minus r times sine hyperbolic square theta. So this is r times cos hyperbolic square theta minus sine hyperbolic square theta. And now if we squaring and subtracting, so what will happen? So a plus b whole square, a minus b whole square. So what is a plus b whole square minus a minus b whole square? This is equal to a square plus b square plus 2ab minus a square plus b square minus 2ab. So basically we left with 4ab. So 4ab means 2ab means 2. 2ab means 2. So 2 plus 2, 4. 4 divided by 4 is 1. So its value comes out to be 1 only. So what is the Jacobian of transformation? In this case also it comes out to be r. But now I need to find out Jacobian of fy with respect to r and theta. Now because f is unknown, so this is curly f upon curly r, curly f upon curly theta, curly y upon curly r, curly y upon curly theta. So simply first row no change, it remains the partial derivative only. The derivative with respect to it is sine hyperbolic theta and r cos hyperbolic sine hyperbolic theta r cos hyperbolic theta. So it is r cos hyperbolic theta curly f upon curly r minus sine hyperbolic theta curly f upon curly theta. So Jacobian of xf with respect to r and theta is curly x upon curly r curly x upon curly theta curly y upon curly r curly y upon curly theta. So this is cos hyperbolic theta r sine hyperbolic theta. This is curly f upon curly r curly f upon curly theta. So we expand this. This is cos hyperbolic theta curly f upon curly theta minus r sine hyperbolic theta curly f upon curly r. So now, so what is curly f upon curly x? So curly f upon curly x, this is 1 upon Jacobian time curly of fy with respect to r and theta. So Jacobian is r and its value comes out to be r cos hyperbolic theta curly f upon curly r sin hyperbolic theta curly f upon curly theta. And curly f upon curly y is 1 upon j times curly of xf with respect to r and theta. This is 1 upon r. This is cos hyperbolic theta curly f upon curly theta minus r times sin hyperbolic theta curly f upon curly r. So what we need to do, we need to square and subtracting. So if we square this one, is we need to square this one and we subtracting and subtracting. So it means curly f upon curly x square minus curly f upon curly y square. So if we are squaring and subtracting, so 1 upon r square is common. So this is r term, this is r term. Okay. So curly f upon curly r whole square, its coefficient is because squaring and subtracting. So this is r square cos hyperbolic square theta minus r square sine hyperbolic square theta. Okay. Because if I squaring and adding, this is 1 upon r square, this is a square, r square cos hyperbolic square theta curly f upon curly r square plus sine hyperbolic square theta curly f upon curly theta whole square minus 2 time r cos hyperbolic theta sine hyperbolic theta curly f upon curly r curly f upon curly theta, right? So this term are square terms are always positive, but because when we take difference, then we get a negative side here. Okay. Now we are considering the second term, that is the coefficient of curly f upon curly theta square. So what its coefficient is? This is positive and this is negative sine hyperbolic square theta minus cos hyperbolic square theta. Next term is the product, means curly f upon curly r into curly f upon curly theta. What its coefficient will be? In this case, its coefficient will be minus 2ab. Here it is minus 2ab, means minus 2r cos hyperbolic theta sine hyperbolic theta. But this is also minus, but because already we have a negative sign, it becomes plus 2 times cos hyperbolic theta sine hyperbolic theta. This term get cancelled out. And because here we have discussed that cos hyperbolic square theta minus sine hyperbolic square theta is 1. This is 1. So if this is 1, it means here r square is common. This is 1, but this is minus 1. So if we calculate this, it will gives us curly f upon curly x square minus curly f upon curly y whole square. This is 1 upon r square times r square common into 1 into curly f upon curly r square. And here it is plus curly f upon curly theta whole square into minus 1. So if I open this bracket, this is curly f upon curly r whole square minus 1 upon r square curly f upon curly theta whole square. So this is the relation between curly f upon curly x square minus curly f upon curly y square in term of r and theta. So this is the desired, right? So here we have discussed the case that if we want to express that we are given that f is a function of x and y they are function of r and theta, but we want to express f of x and f of y in term of r and theta, then we can use here the concept of change of variable, and hence we come up with a solution. And this kind of problems are there where we actually use the concept of change of variable. Okay. I hope it will be clear to you that how do we calculate the Jacobian of transformation of a function, what is its application, and how do we use it to solve the problem of change of variable. Okay, so just practice some more problems based on this particular topic. If you still find out any doubt or any query, you can post your queries. I'll try to provide you the solution. Thank you.